All right, so get ready because today we are going deep into something I know you've been curious about. Einstein's theory of relativity.
It's definitely one of those topics that can really make your head spin.
It can, but that's why we're here. We're going to untangle it together. You actually sent in a podcast episode you wanted us to look at, relatively speaking, how Einstein changed our understanding of time and space. Specifically, it was the episode Theory of Relativity, a journey through time and space with Deep and Shri.
Sounds fascinating.
Yeah, and we're going to use it to jump into this wild world of time dilation, warped space, even those mysterious black holes.
You know, it's so interesting how relativity is just one of those things that everyone's heard of, but a lot of people think it's just way too complex to ever really wrap your head around.
Right, but not us, not today.
We're going to try to break through that barrier today.
And the thing is, before Einstein, everyone thought about the universe in a totally different way. It was all about Isaac Newton, his laws of motion, gravity as this force, pulling things together.
Yeah, Newtonian physics was a huge accomplishment. It explained the everyday world really well. Yeah. Planets going around the sun, apples falling from trees. Newton had it figured out. But then scientists started looking deeper, especially at light, and they started finding problems with the Newtonian picture of the universe.
Yeah, the podcast that we are using for this deep dive pointed that out too. Scientists knew that light was like a wave, but they couldn't figure out what it was waving in.
Right. It's like trying to picture an ocean wave without the ocean. So they even made up this idea called luminiferous ether to fill space and give light something to wave through. But the experiments, they just couldn't prove that this ether actually existed.
It's a huge puzzle. And then enters Einstein. He was totally fine with questioning all those long-held assumptions. In fact, the podcast even mentioned that Einstein wasn't always thought of as a genius.
Right.
He even had problems in school.
Yeah, that's right.
Wait, really? The dude who changed physics struggled in school.
It's true. His genius wasn't really about memorizing facts or always following the rules. It was about seeing the world in new ways. You know, challenging the rules that everyone just took for granted.
It really makes you think, what if our failures or those times we don't follow the normal path are actually the times we can have the biggest breakthroughs?
That's a really interesting way to look at it.
So back to Einstein and his huge changes to physics. The podcast hosts, Deep and Shri, explained that one of the biggest things Einstein tackled was the speed of light. Newtonian physics said that speeds should add up, like if you throw a ball on a train that's already moving. But light just doesn't follow those rules.
Right. Imagine you are standing still and you see this beam of light go by you, and it's traveling at about, well, nearly 300,000 kilometers per second. And now imagine you're running towards that light. You would think that that light would seem to be moving even faster, right? But it doesn't. It's still moving at the same speed.
That is so weird. Why wouldn't it seem faster if you are moving towards it?
That was exactly the puzzle that Einstein solved. And his answer was what we now call the special theory of relativity. And this theory just completely throws out the old idea that space and time are the same for everyone, no matter what. Instead, they are relative to how the person observing them is moving.
Okay, I feel like my brain is starting to bend a little bit here, but I'm with you. So how does time being relative, how does that actually work?
One of the most, mind-blowing consequences of that is something called time dilation. So imagine that you are on this spaceship and you are cruising at a good chunk of the speed of light.
Okay.
For you, inside the spaceship, time would feel completely normal. But for someone back on Earth, it would look like time on your spaceship is moving slower.
Hold on. So are you saying that time actually changes based on how fast you're moving? But that is just wild. How is that even possible?
It's a very real thing, and we've actually measured it. The podcast used the example of atomic clocks on airplanes. Because those clocks are moving, they actually tick a little bit slower than clocks on the ground. And it's not just a theory. It's something that we can actually measure.
Whoa. Okay, I am having a little trouble wrapping my head around that. What about the other weird one, length contraction? I think the podcast talked about that too.
Yeah, length contraction means that things that are moving super fast, they actually look shorter in the direction they're moving to someone who is standing still. So that spaceship you're on, for someone watching from Earth, it would look shorter to them than it does to you on board.
So it would look to someone on Earth like the spaceship has been squished. Is that like an optical illusion, or does it actually change?
It's not an illusion. It's an actual physical change because of how space and time are kind of warping. And to really understand that warping, we have to talk about another important idea from Einstein, space-time.
Okay, let's dive into space-time. It sounds intense.
So try to picture a trampoline. Now put a bowling ball right in the middle. That bowling ball is like a massive object, like a star or a planet. And what it does is it makes the trampoline warp downwards, right? Makes a dip. That dip is the curvature of space-time that's caused by the object's mass.
Okay, I'm picturing it. So smaller objects like planets orbiting a star, are they just following the curve of space-time that's created by the star?
That's exactly it. And that curvature is what we experience as gravity. So instead of thinking of gravity as a force pulling things together, Einstein showed us that it's really the warping of space-time itself.
So it's not that the Earth is pulling me down with some kind of invisible force. It's that the Earth is warping the space-time around me, and I'm just following those curves.
Exactly. It's such a different way of looking at things.
Yeah, it is. And this brings us to Einstein's general theory of relativity, right? The podcast talked about both special and general relativity.
That's right. Special relativity is all about things that are moving at constant speeds. General relativity takes that and adds acceleration and gravity to the mix.
So general relativity is like the bigger, more complete picture of how the universe works.
Exactly. It gives us the way to understand some of the most extreme things out there, like black holes.
Speaking of black holes, the podcast mentioned something about a solar eclipse back in 1919 that actually helped to prove general relativity. What happened there?
Well, during that eclipse, scientists were able to see that the starlight that was passing near the sun was actually bent.
Bent, like the light itself curved.
Exactly. And this bending was happening because of the sun's gravity. It was warping the fabric of space-time around it, just like Einstein's theory said it would. It was one of the first big pieces of evidence that proved general relativity was right.
Wow, that's incredible. It's amazing how we can actually test these theories that seem so, I don't know, so far out there.
Yeah, and speaking of testing, remember those gravitational waves that we talked about before? Those ripples in space-time that happen because of massive events like when black holes collide.
Yeah, the podcast called them The Sound of the Universe.
Well, in 2015, scientists made this huge discovery. They actually directly detected gravitational waves for the very first time. They used this observatory called LIGO to do it.
So we can actually hear these huge events that are happening millions, maybe even billions of light years away. That just blows my mind.
It's pretty amazing, and it shows how creative humans can be in their desire to understand the universe. And those gravitational waves, they're giving us this whole new way to observe and learn about some of the coolest things out there, like black holes.
Okay, let's talk more about black holes. The podcast said that there are these areas of space-time where gravity is so strong that absolutely nothing, not even light, can get out. How is that even possible?
Well, it all comes down to the curvature of space-time. When a really, really massive star dies and collapses, it can pack all of its mass into this incredibly tiny space. And when that happens, it creates this extreme warp in space-time.
So it's kind of like that bowling ball on the trampoline, but just like way, way more extreme.
Exactly. The curvature gets so steep that anything that gets too close, even light, gets trapped in there and can't escape. And that's what we call the event horizon of a black hole.
So if you go past the event horizon, there's no coming back.
That's what we think. Yeah.
And what about the very center of a black hole? The podcast talked about something called a singularity.
Yeah, the singularity is where things get really, really weird. According to general relativity, the singularity is this point where density becomes infinite and space-time is curved infinitely.
Infinite. Does that even make sense?
That's where our current understanding of physics really starts to break down. Basically, it means that at the singularity, our theories don't work anymore. We need some kind of new theory that combines general relativity with quantum mechanics to really understand what's going on in there.
So it's like the ultimate mystery, this point where everything we know just stops working.
Yeah, in a way it is. Black holes show us both how much we've learned about the universe and also how much we still don't know.
This whole conversation has been mind-blowing. It's amazing to think that these theories that Einstein came up with, more than 100 years ago, have opened up all these new areas of research, and they are still shaping how we understand the universe today.
And the most exciting part is, we're really just getting started.
Speaking of getting started, I remember the podcast also mentioned something about relativity affecting our everyday lives. Is that true?
Absolutely. One of the best examples is GPS. You know those GPS satellites that are orbiting Earth? They actually have to take both special and general relativity into account to give us accurate locations.
Wait, really? I use GPS all the time. How does relativity have anything to do with that?
Well, because those satellites are moving really fast and they're farther away from Earth's gravity, time actually passes a tiny bit differently for them compared to clocks down here on the ground. If we didn't factor in those relativistic effects, our GPS systems would be off by miles.
So Einstein's theories aren't just some abstract ideas that are stuck in textbooks. They're actually built into the technology that we use every single day.
Exactly. It's this beautiful example of how these seemingly complicated scientific ideas can actually have a huge impact on the real world.
It's mind-blowing to think that something as abstract as relativity is baked into the technology we use every day.
It really highlights how science is constantly shaping our world, even in ways we might not realize.
Yeah, it's a completely different way to think about it.
It really is. And I think this brings us to Einstein's general theory of relativity, right?
Hmm.
Because the podcast, I remember it made a distinction between special relativity and then general.
Right, yeah. Special relativity is focused on things moving at a constant speed, but general relativity, it takes that idea and it adds in acceleration and gravity.
Okay, so general relativity is like the bigger, more complete picture of how everything works.
Exactly, yeah. It gives us the framework we need to understand some of the most, I guess, extreme things out there in the universe, like black holes. Oh, okay. Well, speaking of black holes, the podcast mentioned this solar eclipse that happened way back in 1919, and it said that actually helped to prove general relativity. What exactly happened there?
So during that eclipse, scientists were able to observe starlight passing near the sun,
Okay.
and they found that it was bent.
Bent? Wait, like the light itself was curved.
Exactly. And that bending was happening because of the sun's gravity. It was warping the fabric of space-time around it, just like Einstein's theory predicted. It was a really big deal because it was one of the first major pieces of evidence that supported general relativity.
Wow, that's incredible. It's just amazing how we can actually test these theories that seem so abstract, so removed from our daily experience.
It is. And, speaking of testing, remember we talked about those gravitational waves earlier?
Mhm.
Those ripples in space-time that happen when massive events occur, like when black holes collide.
Yeah, the podcast called them the sound of the universe.
Right. Well, in 2015, scientists made this huge discovery. They were actually able to directly detect those gravitational waves for the first time ever.
Really?
Yeah, they used this observatory called LIGO.
Wow, so we can actually hear these huge cosmic events that are happening, I don't know, millions, maybe even billions of light years away. That is just mind-boggling.
It is truly remarkable, and it really highlights the power of human ingenuity and our constant drive to understand the universe. And those gravitational waves, they're giving us a whole new way to observe and study some of the most fascinating objects out there, like black holes.
Okay, well, let's talk a little bit more about black holes. The podcast described them as these regions of space-time where gravity is so strong that nothing, not even light, can escape. How is that even possible?
It all goes back to that curvature of space-time we were discussing. When a very massive star collapses at the end of its life, it can cram all of its mass into an incredibly small space. And when that happens, it creates this extreme distortion in space-time.
So it's like that bowling ball on the trampoline analogy, but just taken to like the extreme.
Exactly. The curvature becomes so steep that anything that gets too close, even light, gets trapped and can't get back out. That's what's known as the event horizon of a black hole.
So once you cross that event horizon, there's no turning back.
As far as we understand it, yes.
Wow. And what about the center of a black hole? The podcast mentioned something called a singularity. What is that?
Yeah, the singularity is where things get really strange, really mysterious. According to general relativity, it's a point of infinite density, a point where space-time becomes infinitely curved.
Infinite. I mean, does that even make sense?
Well, that's where our current understanding of physics starts to break down. It basically means that at the singularity, our theories, they just don't work anymore. We need a new theory, something that can combine general relativity with quantum mechanics to really grasp what's happening there.
So it's like this ultimate mystery, this point where everything we know about physics just sort of collapses on itself.
You could say that, yes. Black holes represent both the incredible progress we've made in understanding the universe and the limits of our current knowledge.
Yeah, this entire conversation has been so mind-expanding. It's amazing to think that these theories that Einstein developed over a century ago have led to so many incredible discoveries, and they're still shaping our understanding of the universe today.
And the most exciting part is we're really just beginning to scratch the surface of what we can learn from them.
Speaking of scratching the surface, I remember the podcast also brought up the idea that relativity actually affects our everyday lives. Is that really true?
Oh, absolutely. One of the most common examples is GPS. Those GPS satellites orbiting Earth, they actually have to take both special and general relativity into account to give us those accurate locations we rely on.
Wait, really? I use GPS all the time. I had no idea relativity had anything to do with that. How does that even work?
Well, because those satellites are moving at very high speeds, and because they are farther away from Earth's gravity, time actually passes a little bit differently for them compared to clocks down here on the ground. If we didn't adjust for those relativistic effects, our GPS systems, well, they would be off by miles.
So Einstein's theories, they're not just these abstract ideas that are confined to textbooks. They're actually woven into the technology that we use every single day.
Exactly. It's a great example of how these seemingly complex scientific concepts can have such a real and tangible impact on the world around us. Yeah, it's a really cool example of how science is always shaping our world, even when we don't realize it.
It makes you wonder what Einstein would think about all the things we've discovered since his time, all the
Yeah.
advancements.
Oh, absolutely. He'd probably be so excited to see how his theories have led to so much amazing research. Can you imagine what he'd think if he could see the first picture of a black hole?
I bet. And I bet he would still have so many more questions. It feels like every time we find an answer in this field, it just leads to even more questions.
Yeah, that's the beauty of science. It never really ends. There's always more to explore and discover.
And who knows what other mysteries Einstein's theories might help us solve in the future, right?
Yeah, exactly.
Well, as we're wrapping up this deep dive, I want to make sure that our listeners are walking away with the most important parts. What are the key takeaways that you think everyone should remember?
Well, I think the biggest takeaway is just how much Einstein changed the way we understand the universe. He completely broke apart that old idea of absolute space and time, and he showed us that these things are actually intertwined and they depend on who's observing them.
It's like he opened up this whole new dimension of reality that no one had even thought about before.
Yeah, you could say that. And not only did his theories change how we see the universe, but they also led to some pretty awesome technological advancements that we get to use every day.
So relativity isn't just some abstract concept that's stuck in textbooks. It's a part of our world.
Exactly. And I think maybe the most inspiring takeaway is that Einstein's journey shows us that it's okay to question things and think outside the box,
Yeah.
because that can lead to some seriously revolutionary discoveries.
It's a really good reminder that even those ideas that seem impossible might actually be the key to understanding our universe in a completely new way. It's been an amazing journey exploring this mind-bending world of Einstein's relativity with you.
I agree. It's a great example of how human curiosity can lead us to such incredible discoveries about the cosmos.
To our listener, we hope that this deep dive has made you even more curious and inspired you to keep exploring this topic. Never stop questioning, never stop learning. And who knows, maybe you'll be the one to make the next big breakthrough. Thanks for joining us on this incredible adventure. Until next time.